Okay, the Chapter 6 review. People who eat eggs that are contaminated with salmonella can get food poisoning. A large egg producer takes a random sample of about 200 eggs from all the eggs in one day. So our sample are the 200 eggs selected, representing the population of all eggs that day. Okay, and then they identified 9 of these eggs had salmonella. So you could say, the statistic we got is the 9. We're going to call it a proportion of 9 out of the 200. Okay, we'll call it a p hat. And that's going to represent the true proportion of all eggs. Okay, for number 2, author has written 5 children's books, and the number of pages in these books are listed as these 5. List all the 10 possible simple random samples of size 3, calculate the median, and then display them in a dot plot. Okay, so I took these 5 and I just kind of worked across. I did these 3, and then this one, this one, and this one, this one, this one, this one, and I just kind of went systematically through to get these 10 here. Okay, and then the dot plot. Let's see, let's go 60, 70, 80, I don't just make it up. Actually, I could go 65, 70, 75, probably 75 here. Okay, so the median here would be 66. Median here would be the 71. Median here, 71. Median here, 73. Median here is 66, 71, 71, 66, 73, and 73. Okay, so that is my sampling distribution because I have all possible samples there in that. Part B asks us to show that it's biased, and the way that we can show that it's biased because our population median is equal to 71. And our sampling distribution okay, so this is our sampling distribution. The mean, okay, the mean of all these, okay, is at 70.1. They're not the same. Therefore, it is a biased estimator. It's close, right? The mean of all these medians are close, but it's not equal to 71. Therefore, we consider it biased because it's not the same. Okay, part C, it says if I make it a size 4, so if I take 4 instead of 3 here, remember if I take 4, the sampling distribution, if I take more, it becomes more accurate, so it'll be more condensed, right? With a larger sample, the variability will decrease. Okay, so it'll be more condensed together. Number 3 says that according to the 2010 U.S. Census, 24% of U.S. residents are under the age of 18 years old. Suppose we take 500 U.S. residents. X is going to be the number, so we're talking about number of people in the sample who are under 18. Okay, so my mean of the sampling distribution would be n times p. So I would have 500 people sampled and 24% of them. And 24% of 500 gives you 120 people would be my middle, right? That's how many I would expect. With a standard deviation, n times p times 1 minus p. So 500 times 0.24 times 1 minus 0.24. And I'm going to work that out. 500 times 0.24 times 1 minus 0.24 gives me 91.2. That would be my standard deviation. Okay. Part B, interpret the standard deviation. The number of residents, or U.S., yeah, it says residents, out of 50, out of 500 would vary from the mean of 120 by about 91.2 people. Okay. Part C, justify that it's appropriate to use a normal distribution. So n times p and n times 1 minus p. Got to find those. We know n times p was 500 times 0.24, which was 120 people. And 500 times 1 minus 0.24 gives us 380 people. They're both greater than or equal to 10. Therefore, we can say the sampling distribution is approximately normal. Okay, so using that normal distribution then, how many of those 500 people, what's the probability that I would have between 100 and 110? So I know that I'm going to go to Desmos, right? I know my mean is at 120 with this standard deviation. And I want to know between 100 and 110. So let's say there's 100, there's 110. I want to know that probability right there. So I'm going to go to Desmos, use a normal distribution to get that, and I'll show that video here.
Okay, so we had said it's approximately normal, so we can go to the distribution and go to the normal. We said our mean was 120, and our standard deviation was 91.2. We want to find it in between 100 and 110 would be about 4%.
Okay, number 4. Report claimed that 20% of respondents subscribed to the 5-second rule. That is, they would eat a piece of food that fell onto the kitchen floor if it was picked up within 5 seconds. Assume this figure is accurate for the population of U.S. adults. P hat is the proportion of people who subscribe to this 5-second rule of size, from a simple random sample of size 80 from this population, okay? So now we're talking about proportions, okay? So the mean of all my p hats is going to equal the same as the proportion of the whole thing, of a whole population, which was 20%. And our standard deviation of our p hats was the square root of p times 1 minus p over n, okay? Which is the square root of 20% times 1 minus 20% over a simple random sample of 80. Okay, I'm going to use my calculator. You guys will use Desmos. And I get a standard deviation of 0.0447. Okay, so that's part A. Part B, interpret the standard deviation from part A. Okay, so part B, the proportion of those who agree with or would use the 5-second rule would vary from the mean of 20% by about 0.0447, about 4.5% almost. Okay, C, is it appropriate to use normal distribution? We know that n times p and n times 1 minus p have to be greater than or equal to 10. Okay, so here we have 80 is my sample times p. So 20% of 80 people would be 16 people, and 80 of 1 minus 20% is 64 people. Okay, both are greater than or equal to 10. Therefore, I know my shape is approximately normal. Okay, So then part D, we know our shape is approximately normal. We said our mean is at 20% with a standard deviation of that there, of 4%. So part D, only 10% prescribed. So they took a sample and they only got 10%. Does it give convincing evidence the proportion of U.S. adults is less than 20%? So it gives a little bit of evidence, but could have just happened, okay? So we got a sample of 10%. So I want to figure out this area right here. Okay, so I'm going to go to Desmos and do that.
Okay, so we said it was normal, approximately normal, so normal distribution. Our mean was 0.2 with 20%, and our standard deviation was 0.0447. Okay, so there's our graph, and we want to know 10% or less, so from negative infinity to 10%. That gives us the probability that it's less than 10% was 0.013. Okay, so not very likely to happen, right? So if it really is 20% and we get this sample, that sample is not very likely to happen. So therefore, our conclusion would be it's probably not 20%. There's good evidence that it's less than 20%.
Okay, so we said this sample would only happen 1% of the time. If it really is this, therefore it gives us good evidence that this is not true, that it is less. Okay, number 5. Number 5, Wechsler Adult Intelligence Scale is a common IQ test for adults. The distribution of the scores for persons over 16 years of age is approximately normal, so we know our population is approximately normal, with a mean of 100 and a standard deviation of 15. Let x bar equal the mean of a sample of 10 people. Okay, sample of 10 people. So the mean and the standard deviation. So for part A, the mean of all those x bars is going to equal the same as the mean of the population, which is 100, mean score of 100. And our standard deviation is going to be this standard deviation of our population divided by the square root of n. So our population had a standard deviation of 15. And I'm taking a sample of size 10 people. Okay, so go to your calculator. 15 divided by the square root of 10 gives me 4.74. Okay, so there's my mean and my standard deviation. For part B, interpret the standard deviation. Okay, so we'll interpret again. The average score varies from the mean of 100 by about 4.74 points. Okay, part C. What is the probability that the average score is 105 or greater? Okay, 105 or greater. The probability that the score is 105 or greater, so greater than or equal to 105. So we know that it's approximately normal because it says our population was approximately normal, so we're okay with there. So we can go and find it here. So from our graph, we know our mean is 100 with this standard deviation, and I want 105, 105 or more is that area there I want to find. Okay, so I'm going to go to Desmos and do that.
Okay, so our population was normal, so our sampling distribution is going to be approximately normal. We said our mean was going to be 100, standard deviation of 4.74. Okay, so there's our distribution. And we want to know, it says greater 105 or greater. So 105 or greater to infinity gives us about 15%. Okay. There's my answer for part C. And part D, with the answers to, okay, so we'll answer that back on the paper.
Okay, so one thing I'm mistake, 105 would be here and above, not over here. So I just got a number line wrong, right? 105 would be there. All right, anyway, part D. Would this change, would A, B, or C change if I knew the population was not normal? Okay, so this wouldn't change. A, no change. Okay, B, no change. But C would change because if I know the population is not normal, then I have to use CLT, which means I have to have a population of, a sample of 30. I only have a sample of 10. So therefore, it would not be normal. Therefore, I can't use a normal distribution. So I can't, it would have a different probability. Okay. Number 6. The gypsy moth is a serious threat to oak and aspen trees. A state agriculture department places traps throughout the state to detect the moths. Each month, a simple random sample of 50 traps is inspected. The number of moths in each of the trap is recorded. So our N is 50 here. The mean number of moths is calculated. So we're talking about means here. Based on years of data, the distribution of moth counts is strongly skewed. So our population is not normal, but we're taking 50, right? So it's above 30, therefore we can say the sampling distribution is about that. Has a mean of this and a standard deviation of this, okay? So the population has a mean of 0.5. We know our mean of all of my x bars is the same as the population, 0.5. The standard deviation is going to be the standard deviation over the square root of n. So we said the standard deviation here is 0.7. And our sample, we're taking a sample of 50. Oop, can't see that. Okay. So we're going to have 0.7 divided by the square root of 50 gives us 0.099. Okay, so we have our mean and our standard deviation. Okay, part B, calculate the probability Oh, I did the wrong part there. So explain why it is reasonable to use a normal distribution to approximate the sampling distribution. So for part A, we can use CLT. Okay, sample is more than 30, therefore the sampling distribution is approximately normal. Okay, so we know it's going to be approximately normal because of CLT, samples above 30, has a mean of 0.5 and a standard deviation of 0.099. Okay, so then for part B, calculate the probability that the mean number of moths in a sample of 50 is at least 0.6. So we want at least 0.6, will be 0.6 and more. We want to find that probability there. Probability that x is at least 0.6. I'm going to go to Desmos and find that again.
Okay, because of CLT, we know it's approximately normal with a mean of 0.5, comma, standard deviation of 0.99. Okay, and I want to find the probability of 0.6 or more. So from 0.6 through infinity. Okay, gives me a probability of about 16%. Okay, so I get 0.16 is that probability there.
Okay, and then part C. In a recent month, the mean number of moths in a simple random sample of 50 was 0.6. Based on this result, should the state be worried that the moth population is getting larger? Okay, so if it really is 50%, and I got a sample of, or not percent, if the mean was 0.5, but I got 0.6, is that enough evidence to say that this is wrong? Okay, I would say no. 0.6 could happen just by chance. Okay, and there's a 16% chance of that happening, right? So that's not enough evidence. If it was like 1% or 0.1%, I'd say yes. It's not this, it's getting larger. But at 16%, it could have just happened by chance. It could still be 0.5.